The moment of inertia, also called the rotational inertia, although I will be calling it moment of inertia throughout the video, appears in a number of equations when dealing with rotational motion, especially rotational motion of rigid bodies. We also know that these equations don't hold in all cases, but they require something about symmetry axes. What is moment of inertia, and what does symmetry have to do with it? That's what this video will explore. So firstly, this moment of inertia that appears in these formulas is calculated about an axis, namely, it is calculated about the rotation axis through the reference point for which you are calculating angular momentum and torque, for example. R in these moment of inertia equations are the perpendicular distance from the axis of rotation to one of the masses or one of the infinitesimal masses on the rigid body. If you consider the equation torque equals I alpha, you can see that moment of inertia is the rotational analog of mass. It quantifies how difficult it is to make an object rotate with a given torque. For a given torque, if there is a bigger moment of inertia, the harder it is to rotate. And for the same given torque, the smaller the moment of inertia is, the easier it is to rotate with that torque. If you consider the formula for the moment of inertia, where we have these r squared times masses, right? These r squared times masses, then you can see, if you know statistics, that the moment of inertia is a measure of how mass is distributed or spread about an axis. This formula right here is a second moment. It is also additive. If you want to find the moment of inertia of a more complex object or of multiple particles, then the total moment of inertia about an axis of rotation is just the sum of individual moments of inertia of each component about the same axis. So for an example, if we have a disk with a point mass stuck to it, if we want the total moment of inertia of this disk plus point mass, just find the moment of inertia of the disk about the axis of rotation in red, then find the moment of inertia of the point mass about the axis of rotation in red, add them up together, and that's the total moment of inertia of this system. However, although it is the rotational analog of mass, it differs in one very important aspect, and that is that, in general, it is not a scalar quantity, but a quantity known as a tensor. And this tensor is defined about a reference point, not a rotation axis through the reference point. So just like torque and angular momentum, the moment of inertia tensor is defined about a reference point, not a rotation axis. It's important to note that it is a tensor, not a scalar, because these equations that we use, they all assume that moment of inertia is a scalar. They will not hold in general. However, if you make moment of inertia a tensor, some of them will still hold if you treat the moment of inertia as a tensor. So these vector equations for angular momentum and torque, if the moment of inertia is a tensor, where all the quantities are defined about the same reference point, torque and moment of inertia tensor about the same reference point, these equations will still be true when moment of inertia is a tensor. But on the other hand, the rotational kinetic energy formula, that will not be true when I needs to be treated as a tensor. So moment of inertia being a tensor or a scalar can affect whether these equations are true in general or not. Furthermore, one interesting property about tensors is that when you multiply it by a vector, the output vector doesn't need to point in the same direction as the input vector. And so, for an example, when I is a tensor, this angular momentum equation, treating I as a tensor now, not a scalar, does not mean that angular momentum and angular velocity point in the same direction. So that means, although this equation holds in general when you make moment of inertia a tensor rather than a scalar, angular momentum and angular velocity do not in general point in the same direction. Same thing with torque and angular acceleration. Whereas if moment of inertia was a scalar, then all we're doing is rescaling this vector, and moment of inertia will always be a positive quantity, so it'll be rescaling it without changing its direction. And so if you have a positive constant times a vector, you end up with another vector that points in the same direction. If moment of inertia is a scalar, then angular momentum and angular velocity will always point in the same direction. Same thing with torque and angular acceleration. In this course, though, we will only deal with simplified cases where we can treat moment of inertia as a scalar rather than as the full tensor quantity. So we'll only be dealing with cases where angular momentum and angular velocity point in the same direction, and likewise when torque and angular acceleration point in the same direction. In this case, the moment of inertia as a scalar is not defined about a reference point, but rather about an axis of rotation through the reference point. So you need to calculate the moment of inertia about the axis of rotation. You can't just treat moment of inertia as a scalar, though, without some condition. The first condition is that the rotation axis about which you are calculating the moment of inertia needs to be a quote-unquote symmetry axis through the center of mass, or if the axis is through another point, it needs to be parallel to a symmetry axis through the center of mass. By symmetry is meant rotational symmetry about the axis. So for an example, consider this cylinder with this axis of rotation that I have drawn through the center of mass. This is a symmetry axis. You can rotate this cylinder about the axis and it will look the same. Or another way to think of it, if I take one mass over here and calculate its angular momentum about a point through the center of mass, I can find another point on the opposite side of the axis and calculate the same. I can calculate r cross p for both of these, and what will happen is that the components of angular momentum that are not along the axis of rotation will cancel, leaving with just one angular momentum that is about the symmetry axis. So this is the rotational symmetry that is desired. The idea is that the masses balance each other across the axis, so the angular momentum can cancel out. If the axis of rotation is through another point, like here, or even outside the body here, then they need to be parallel to a symmetry axis, such as this one. If I had an axis like this, that is not parallel to a symmetry axis, that would not allow us to treat moment of inertia as a scalar. Similarly, here's an axis that goes through the center of mass, but clearly it is not a symmetry axis. The cylinder does not have a rotational symmetry about it. There isn't a mass on each side that can balance each other out and cancel components of angular momentum. So this would be another example of an axis we can't use if we want to treat the moment of inertia as a scalar. Another consequence of requiring a symmetry axis has to do with the angular velocity. Recall that the rotation axis is defined by the direction of the angular velocity of your object. Therefore, since we need a symmetry axis, the angular velocity must also point in the same direction as a symmetry axis. For symmetrical mass distributions, such as objects with a uniform mass density, or the cylinder that we just considered, assuming it had a uniform mass density, you can find the symmetry axes pretty intuitively, and it will align with the geometry. I knew that the axis that I drew was a symmetry axis. It very intuitively aligns with the symmetry of the cylinder. I could also create a symmetry axis like this, bisecting the cylinder in that direction, and I could also bisect the cylinder by an axis that comes into and out of the page, right through the center of mass also. All of these are very intuitively axes of symmetry for the cylinder. So long as you have a uniform mass density, the symmetry axes can be found pretty easily. They align with the geometric symmetry of the object. So that's it. That's what you need to treat moment of inertia as a scalar. You need the rotation axis to be along a symmetry axis. You need the angular velocity to be along a symmetry axis, and then you can do it. If you're curious, symmetry, although it is a consideration, it isn't the main thing. The thing that will exactly allow for treating moment of inertia as a scalar is when the rotation axis is a principal axis, or an axis that is parallel to a principal axis. Dealing with these in detail are beyond the scope of the class, but a few words about them here. The first thing is that every rigid body has 3 mutually perpendicular principal axes, even if the body itself is not symmetrical, and all these axes go through the center of mass. So for an example, using the cylinder again, although it is a symmetrical object, we found 3 symmetry axes that go through the center of mass. We found the one that goes up and down longwise, we found the one that goes horizontally through it, and then another one that goes horizontally through it, bisecting it, that comes into and out of the page. All 3 of these are perpendicular to each other. These are the principal axes for a cylinder. A cylinder, though, is a symmetrical object. Any rigid body will have 3 mutually perpendicular principal axes, kind of like this, even though the body might not be symmetrical. We can see from this demonstration with the cylinder that I drew then the following, namely that the symmetry axes for symmetrical mass distributions, so by that I mean mass distributions that have that rotational symmetry about the axis of rotation, those are principal axes. But principal axes can exist even in the absence of symmetry. So you can essentially think of a principal axis as a symmetry axis but a principal axis is a more general concept. A symmetry axis is a special case of a principal axis. So that's all you need then. You need the rotation axis to be about a principal axis through the center of mass, or if the rotation axis is not through the center of mass, the axis of rotation needs to be parallel to a principal axis that is through the center of mass. In those cases, you can treat moment of inertia as a scalar, and that is one of the requirements that we need for the equations that we are used to seeing to hold for angular momentum, torque, and rotational kinetic energy.